Hey, lesson number 26. Here we go. We got working with some more exponents. We got construction background going on in the background here. We got some tools and stuff. I've been doing some work today. You can see I got paint all over me. Just ignore that. I'm going to talk to you today about exponential equations. Let's write that down. Exponential equations. So how is that different than our last lesson? Well, this time we're going to solve equations for the exponent. There's going to be an unknown variable in the exponent, and that's what we're going to solve for. All right, so that's going to be the difference. So let me just show you this real quick and see if this helps you make some logical sense of what we're about to do. If I wrote down that 7 to the third equals 7 to the x, what does x have to be to make that true? This is where I wish I had a classroom. So maybe some kids in the back could fill in and answer questions for me, because this is what's awful about teaching this online stuff is I got nothing. I got no interaction here whatsoever. It's just me and the phone. Oh, and Rainbow Dash is here. I'll put Rainbow Dash up top here and she can maybe answer for me. But anyways, hopefully you can conclude that x must be 3 to make this true, right? So x has to be 3. So the bottom line is, if these bases are the same, then these exponents must be equal. And that is the process we use to solve exponential equations. So let me show you another example of that. Okay, so this time I have 5 to the x plus 1 equals 5 to the fourth. So obviously, if these two are the same, then that must mean that these exponents must be equivalent. That's the only way this is going to be equal. So what we do is we just imagine these 5s aren't even here. We like drop the bases right out and just say, all right, if these are a statement of equality, then these two things have to be equal to each other. So we take x plus 1 and we set it equal to 4. And we just forget about the 5s. And that's a very easy equation to solve. We just subtract 1 from both sides and we get that x must equal 3. And if I plugged a 3 back in here, I would clearly get a correct solution. All right, let me try another one. Gonna get a little bit more complicated. So this time, the two numbers on both sides don't have the same base. They're not the same base. So I can't just simply say, all right, I can just set the exponents equal because this is a 2 and this is an 8. But what we can do is we can take that 8 and write it as 2 to the something to make the bases the same. So that's just going to take a little bit of, quick mental math or even your calculator to figure out what 2 to the what gives me 8. So 2 to the x minus 1 I'm not touching, but 8 is 2 to the third power, because 2 times 2 times 2 is 8. So now it's back to what we just did. So now my bases are the same. Both got 2's, which means these two things must be equal. So x minus 1 must equal 3. Add the 1 over, and I get that x equals 4. So that's going to require a little bit of manipulation. All right, I'm going to do another one that's going to require a manipulation on both sides. So this will be the last one that I do. This is going to be the most complicated one. Before I do that, since we have the construction theme going on here, I wanted to show you a quick video. I've been doing some work around the house, getting stuff done, taking care of all the things that I've been trying to get done in my house for the longest time, and have a little bit of time to do now. Took a time-lapse video of myself installing 2 new lights and some ceiling tiles in my basement. So enjoy. Hope you enjoyed. Wasn't the greatest thing in the world. Not as exciting as copper. Not as exciting as Rainbow Dash. Not as exciting as my bat. Not as exciting as the keyboard, which I still haven't forgotten. I have and can smash at any time here. But it's still exciting. Gives you something to look at. So here's our last example. This one's going to require more work than the others. I have a 9 on the left side and a 27 on the right. Now, there's no way for me to take 27 and write it as 9 to the something. You might be thinking, oh, well, 27 is 9 to the third. No, it's not. 9 times 3 is 27, but 9 to the third power is not 27. So when this happens, we have to change both sides. All right, so we got to think about a number that I can raise to a power to get 9 and 27. And this would be the moment where I ask the class, can anybody think of a number? And someone will yell it out or raise their hand and have the answer, but I got nobody here. So I'm just going to tell you, I can write 9 and 27 both with a base of 3 to the something. Because 9 is 3 to the second, and 27 is 3 to the third. So you just have to be able to look at it and see that and figure that out on your own. You got to figure out what base you can work with. So I'm going to take this 9 and change it to 3 to the second, and it's still being raised to the x plus 1. So all I've done is change the 9 to a 3 squared. The 27 I'm going to change to a 3 to the third, and that's still being raised to the x. Now we got to go back to our original exponent laws, which say that if you have a power raised to a power, the rule is you multiply your exponents. So these need to get multiplied and these need to get multiplied. So what's going to happen is this is going to turn into, when I take this 2 and multiply it into x plus 1, it's going to be distributive property. It's going to be 3 to the 2x plus 2. This, when I multiply these two, is going to turn into 3 to the 3x. Now it's back to where we started originally. I've got the bases the same, which means logically these exponents must be equivalent. So I can take the 2x plus 2, set it equal to 3x, and solve that equation. Pretty easy equation to solve. Just got to get x by itself, get x's on one side, probably just subtract the 2x over. That's going to be the easiest. That's going to leave me with a 2 here and then just an x here. So x equals 2. This problem's done. All right. So the whole key is being able to recognize what base I need to drop these things down to in order for them to work. I'm going to erase and just discuss one last thing with you real quick. Okay, so being able to get the bases the same is the whole key, like we said. So let's just say, for example, you had 25 on one side and 125 on the other. You need to be able to look at that and go, okay, there's got to be a number raised to something that I can get on both sides. And you just need to be able to, look at it. You got to kind of know your times tables and know your multiplication rules and things like that. But this 5 could be turned into 5 to the second. 125 is 5 to the third. And that would get you your equivalent basis. So those are the things you got to be thinking about as you're solving these exponential equations. Now, normally in class, the next logical question, I always tell you guys in class who's got the $5 million question. The $5 million question in this whole lesson is, Mr. Griska, what happens if I can't get the bases the same? All right, and that's a great question, and I'm sure some of you might even be thinking that, and that's awesome. What do you do if you have 3 to the x on one side and maybe 7 to the 4x on the other side? I can't get those bases the same. I can't change 7 to 3 to the something or anything like that. So how do you solve something like that? Does it mean it's not solvable? The answer is, it is solvable. But to do it, you need a logarithm. And we're going there very soon. We're going to start talking about logarithms, and they're going to be helpful when we try to solve equations like this. All right, so that's what's coming, sneak preview. Good luck on the homework.